So let's start with the new session about start from the scattering and the transmission theory. So actually this part has two lectures, but because the content is rich, I will separate them into two. So I would tell you why we need a laser with passive region. They have actually many functions. They are not burdened. Sometimes you have a segment of unpumped region is very beneficial for some application. And the second, we will discuss the formalism for the scattering matrix and the transparent matrix. That will help you evaluate the reflectivity and the transmissivity of the passive region. Yeah, and we will, according to the property of the scattering matrix, we can define the network with some specific type. Then we will see what's the application on the common vector type laser. So in lasers, there will be some part which the pumping level is intentionally lower or even no pumping. And we call that passive region. Those with the high pumping, just like the engine in the car, yeah, it's the active region. But those with the lower the pumping or zero pumping is the part called the passive region. So the one example of the passive region is the modulator. For example, we can let a laser in two segments. And the one is with a high pumping, so it generated light. And the other one with the same material, but it is unpumped or even reverse biased. So that unpumped material will be an absorbing region. So while you trying to transmit some information from laser like 101010. One way is to modulate the current here. But there's a disadvantage that while you are changing your current, the characteristic of this laser also change. So probably the wavelengths might also shifting a little bit, or the temperature will be shifting. So some people try to decouple this part. The first part is we just inject a constant current, so there will be light emitting from the active region. But we only change the passive region with different reverse voltage. So because this part it is unpumped, but its property, its absorption value might be modulated by the voltage. So that will be keeps sending one the information of one continuously, but chopping them. Because if you increase the absorbance of the passive region, you can change the one into zero with a rather stable property of your the light input from the active region. So that's one purpose you might want some part of laser without strong pumping. And another very classic or conventional passive region is the DBR. Distributed breadth reflector. It's a multi-layer structure with alternating refractive index. So if you design the thickness right with some criteria, you can enhance the reflectivity of specific wavelengths almost into one. So in this case, you can reduce the mirror loss of your ball laser and reduce the threshold current density. So this is almost can be observed in all semiconductor lasers with a decent performance. Yeah, because we want to reduce the mirror loss. And this we also often hear the word about grating. Grating is also a type of DBR, but that's only because the structure looks like a conventional grating in the optics. The grating is also an alternating structure with different refractive index. But while we call it grating, it usually has a much smaller counter refractive index. For example, in DBR, we usually discuss with two different materials, like For example, this might be SiO2 and the other one might be TiO2. But while in grating, we usually discuss the material only have a minor difference, probably a little bit thicker and a little bit thinner. And probably a little bit, the consumption will be lower, like our case, if the aluminum only increase a little bit. Yeah, in this case, your refracting index difference will be much smaller. And with a much smaller contrast in refracting index, basically the reflectivity will also be less. But the best merit is if you can construct a mirror with a very small delta N, you will get a very narrow band. Then you can choose your wavelength of your laser. So depends on the purpose you want. If you want to build a very high reflectivity with less care, then we need a alternating structure with large delta N. But if I only want to choose a very small region with high reflectivity, then we need to do grating. Which means we need to changing the reflectivity only a little bit, but doing more pairs. You can still construct a relatively high reflectivity, but and that will also give you a capability to choose the lasing wavelengths. We will discuss that in detail in the next lecture. So, in order to describe the whole plastic region with a more generalized formalism, we introduce something called scattering theory. We can consider a system is pretty arbitrary, so it's only a schematic feature, and it has so many ports. That port means this is where the energy will enter or leave. So probably you have a port 1, port 2, port 3, port 4. And we call that the entering port as A, and leaving with B with a subscription of number in the number of ports. So then we consider this as the cavity, because conventionally there's also some people use scattering matrix in circuit. Yeah, they will describe a part of the circuit as the scattering matrix. Then the input is current and output is current. But now we are doing lasers, so we consider this system to be a cavity for light. Then the input will be electric field, and output also will be the electric field. So the scattering field describes how the energy is how the energy is entered or scattered in the other pole with a linear relationship. Okay, so because we need to describe that in energy, so we cannot use the in vector only as the electric field, because the electric field square doesn't direct those two, the energy. The energy is electric field times the magnetic field. So we actually assume the input vector AI as the field of the electric field times its propagating term. And the most important, we need to divide a term to the 2 eta. The eta I here is not the injection efficiency. Don't mix with the eta I from the last lecture. The eta I is actually the ratio between your electric field and the magnetic field. And according calculation, that will be 377 ohm divided by your refracting index. Okay, so that's part of electromagnetism. So we'll just use this assumption. So if we do this, we can double check whether AI squared is in the unit of power. So if AI is the electric field divided by square root 2 eta, then AI conjugate and AI, that means its absolute value, will be eta I squared divided by 2 eta I. And the eta I is the ratio between electric field and the magnetic field. So it becomes E times H divided by 2. So this is the form of the power flow according to the Poynting theorem. So remember that there will be a part of the delta N in the denominator. This is the real input vector, not electric field only. Okay, so we assume that the output power is the linear combination of input power. Like the power of the vector 2, of the port 2, output power from port 2, shall be the summation of power input from port 1, port 2, port 3, just depending on how many powers, with a coefficient. So we just use the linear model. So probably in real world it is not linear, but we can the linear algebra is much more easy. So we will usually use a value with a linear term. Yeah, we don't have like a Sij aj squared. No, we don't have the higher order term. We just take a linear term. Okay, so according to the formalism here, how do we find the Sij experimentally? We can just consider a theoretical experiment, which is that if we only input power from port J and then no power from else terms, then we can try to find all the power from different ports. That's you have only one input and evaluate the outputs. Then you can, and you divide these two terms, you will get the Sij. Yeah, this is in the formalism of the matrix. Alright, so we can put OI and the BJ together as a matrix format. So the BI is the vector of the output power. So it will look like, okay, so already here. The output power from port 1 is this big matrix times the output power from input power from 1, 2, 3 to n. So if you have n ports, your scattering matrix will be n by n matrix. Let's take a quick example. Let's consider a very simple very simple system called a dielectric interface. So this only interface and there's a two port. A1, B2, B1, A2. So if this interface is your cavity, the light goes in toward the interface by A. The vector leaving the interface is noted by B. Alright. So according to the S11. S11 means when there's the input power from A1 and there's no input power from A2, and what's the output power from B1? Yeah, since there is no input from here, there's only input from A1, and we will see the power from B2. So basically, this is reflectivity. So it will be. We write it down more specifically. So N11 is E square root N1 exponential blah blah blah. Just keep that. And E out. No, B is in the top, on the top. So because it's from on the other side, so reference index is the same, and the exponential So basically, it is E out from E in, which means the reflectivity of the field. So according to the interface and the Fresnel equation, it should be N1 plus N2 N1 minus N2. Okay. So similarly, we can see that S22. S22 is when there's no input from the dielectric one. The power leaving the interface while you have some energy going inward interface. So it's B2 over A2. That will be the reverse way. N2 minus N1 divided by N2 plus N1. Alright. So the sum of the S12 and the S21 is the term sometimes we will make a mistake. So S21, let's see the S21. S21 means there's no input power from A2. What's the output power of B2 if there's import from A1? So basically that's the transmissivity, but not exactly. Because remember, we have already divided by square root theta I here. So the S21 is the E out square root, because it's at N2, and the exponential. Okay, we can also skip here. And similarly, the E in with square root N1 exponential. Okay, so it looks like the square root N1 over N2 times the E out over E. And this part is the transmissivity. If you use see from the electromagnetism textbook, it is N1 over N2 times N2 times plus N1 divides N2. Yeah, because the leaving is leaving in the N2 side. So it turns out the N2 plus N1 square root N2 N1. Okay. And similarly, you apply the sorry. Okay. Yeah. That's the initial slide. So the S21 is just, you can just changing the notation, the position of 2 and 1. Just switch. Okay, you will get a system. So without loss of generality, we can nest N2 more than N1. So the scattering matrix looks like this. Minus R, T, R. Yeah, since N2 is larger, we can just take this one as the negative value, and this is a positive value. And R is the N2 minus N1 divided by N2 plus N1. And the T is lossless. It will be square root 1 minus R squared. The second example is the homogeneous medium. Means the cavity is just a space filled with something, and it's homogeneous. So the power input from the one side at z is equal to 0. We just write it down, E divided by 2 zeta I exponential minus j beta z. And after propagating with length L, it becomes 0 plus L. So it written like this, because we only replace 0 with 0 plus 0. Okay, the reverse way we can do the same thing, but because the direction is now inverse, so it change from minus to plus here. Remember that we write down beta with a notation like a way here, because that means it could be a complex number. Yeah, if the material is under excitation for semiconductor, it will have the imaginary part, which is here. it will have the imaginary part. So this is the phase term. The imaginary part is relevant to escape. And the gain is model gain subtract its internal loss divided by 2. Yeah. Okay. So we'll see what is the scattering matrix of a bulk material. So the S11 will be there while there is no input from the right hand side. And what's the ratio between the right hand side and the left hand side? So it just probably. Alright, so you just divide these two terms and you will get. Oh, sorry. S11 is while there is no input from the right hand side. What's the ratio between the B1 and the A1? Because there is no input from right hand side, so B1 is 0. So it is just an imaginary interface. You should not have any reflection. So the result is 0. Similarly for S22. Okay, and the S21 is the ratio while there is no input from left hand side. What's the ratio between the B1 and the A2? So it is just a simple propagation. You divide these two equations, you will get the exponential minus J beta L. And similarly for the S21. So the scattering matrix of the homogeneous media is just an of diagonal matrix with 0 at the diagonal side. Okay, so actually these two is good enough for all the case we will encounter in this class. All of them are just trying to the combining interface, the bulk interface, then you can do a multi-layer. Alright, so what's there's some definition of the system. The first is a system. It's called a reciprocal. What does the reciprocal mean? Reciprocal means the physical phenomena observed from any pole should be the same. Yeah. That means the physical phenomena you see from pole 1 should be the physical phenomena you see from the pole 2. So it is interchangeable. So according to the statement, that means no matter how we change the 1 and 2, we shall get the same matrix, because this matrix becomes the physical figure of this cavity. So if a system is called reciprocal, we will see its scattering matrix should be symmetric. Sij should be equal to Sji. Okay, so let's see the interface and the homogeneous media are reciprocal. Okay, see first. It is the same. Because this one, the HG that is also the same. Okay, a simple interface should be reciprocal. That doesn't even matter you are injecting the light from medium 1 or medium 2. It should obey the some fundamental law. And the case of the median, let's see. Yes, sure, obviously it's also a symmetric matrix. Also, both of them are reciprocal systems. Second, if a system called lossless, what does lossless mean? That means the input power, the output power, the summation of output power should be equal to the summation of input power. So let's consider if we only have input power from port 1 or port I. Then you input power into port I and it will scatter into all output ports. So that will be a summation of Bj. So the total input power from 1 should be the summation of all output power. And you change the Bj into Sji and divide the Aj on both sides. So this means the sigma, the Sji squared with the same I and the varying j. That means you are summing the matrix in the same column. S11, S12, S21, and S22. So if you are summing, changing the first one, so that will be S11 squared plus S21 squared equal to 1. And similarly for the second row, second column, S12 squared plus S22 squared equal to 1. So if a system is called lossless, that means the moduli of each column should need to be 1. Okay, so does this hold? If an interface is lossless, which means it's R squared plus T squared need to be 1. Most of the cases, yes, but sometimes for example, your interface have some roughness, or your interface have some absorbing region or absorbing defect. So if it's possibly not equal to 1. So the interface not necessarily be a lossless value. Okay. And similarly, if it's a median to be lossless, it only happens if the 0 squared times exponential minus j beta squared is 1. Okay, this only happens when there's no imaginary part. That means gamma g is equal to alpha. So it's the transparent condition of the semiconductor. So for the interface and the median, they are naturally reciprocal, but not necessarily be lossless. It could be, but not necessarily. Okay, so then we can conclude both. If a system is both reciprocal and lossless, what will it look like? So we need to combine these two properties. First, x1 is equal to x21. Second, x11 squared plus x2 squared should be equal to 2. So, and the x12 squared plus x22 squared should be equal to 1 as well. So the conclusion is that the x11 should be equal to x22. So that means the matrix is asymmetric from of diagonal direction and the off diagonal direction both. Okay. And there's some statement from physics, but we can use that as to derive a mathematical relation in the matrix. If two systems is connected together, so that means the output port of the system 1 is equal to the input port of the system 2. The other way, similarly, the output port of the system 2 is equal to the input port of system 1. Okay, so we can see the input and output from this side and this side, both. And physically speaking, if system 1 is lossless, system 2 is lossless, then the combination of this system definitely should be lossless. Yeah, or where does the energy go? Yeah, since we call it lossless. So if we consider the junction of S1 and the S2 as the even larger cavity, then the scattering matrix of such large cavity at least possess the same mathematical rule or mathematical property in this page. So that will be a boundary condition you can use for while you are trying to assess the exactly shape of the scattering matrix.